Hello everyone. In continuation of our discussion on resistive circuits and equivalent resistors, we're going to move on to some other circuits that are of importance and applications. So this is a specific circuit that you may see later on in a lot of instrumentation. There are situations where a circuit like this would be useful to use, and we're going to touch upon the specific usefulness of the circuit later on. But for now, let's imagine that we have a resistive circuit with the 5 resistors connected to each other in this specific configuration. And let's start by assuming that the question is how to calculate an equivalent resistance for this circuit. So we're looking into these two terminals, and we're trying to figure out what the equivalent resistance is. So to quickly review, whenever you're asked to calculate an equivalent resistance, what that really means is that you put a box around the circuit and you only see two terminals, and what you're trying to accomplish is to look into those two terminals and assume that internal to that box there's only one resistance and calculate the value for that resistance. Assuming that there's no other sources connected to that circuit, then you can put your own source, voltage source here, or current source for that matter, and divide the voltage that is applied across the two terminals by the current that is going into that, and by definition that's the equivalent resistance. So that's what we're going to do here. So I'm going to put my source here. I'm going to call that VT, standing for test voltage, and then there's a current IT going into that, and my plan is to calculate what the equivalent resistance would be. So we're back to basically analyzing a circuit. Like I said, no matter how I describe the question, you're still really deep down asking the same question, analyze the circuit. And once we analyze the circuit, there is everything known about the circuit. But what I'm specifically interested to know about this specific circuit is to calculate VT divided by IT, since the equivalent resistance would be VT divided by IT. Okay. That said, we're going to move on to our algorithm. And by the way, if you're just watching this kind of in the middle of the sequence, the universal approach to our circuit analysis for all of these lectures is explained in lecture number 3, so you can go back. There are 2 parts, and watch that before looking back into how we do it. So we're going to start labeling the circuit. So I identify all the nodes. So this would be one node. This whole thing obviously is one node. This would be another node. This is another node, and that's another node. And now I start naming the nodes. I'm going to assume this one is my reference, the ground. Then I'll get to this one. Like I said, I can either call that one V1 and later on write the equation for that step. Write the equation for this source and say the potential on top is equal to the potential of the bottom plus VT. Or do that right here and say, okay, this is 0, so the potential up there would be VT. And that's what I'm going to do to skip introducing a new variable for the top node. Then I'm going to call this V1 and V2, and that's going to take care of all the voltage nodes. Now, it's time to label the currents. I've already labeled the current that is passing through the component VT, the source. I'm going to keep on doing that for other components. I'm going to call this I1, call that I2, call this one I3, I4. Notice that I'm labeling currents for components. And the direction of the current is completely arbitrary at this point, I5. Now with that, step number 1 is done. We took care of labeling the circuit. Now we'll start writing the equations. So for that, we start by writing KCL. So we have that node that we can write KCL for. these two and the node at the bottom, we can write a KCL for each node. Like I said, the bottom one, you don't have to write the KCL for it. It's redundant. It would end up being the same thing that you write on top. Even though it's correct, you don't need to write that. So for that node, the current going in is IT. There are two currents, I1 and I2 leaving. So IT is going in, and that's equal to I1 plus I2. For this node, I1 is going in, I3 and I5 are leaving. So I1 would be equal to I3 plus I5. And then finally for that node, current I2 and I5 are going in. So I2 plus I5 is equal to I4 leaving the node. That takes care of KCL. Now we have a total of 6 components. So I have a total of 6 equations for component to write. However, I already wrote the equation for that component when I called that VT, so there are only 5 components left. They all happen to be resistors, so the equation for those to us are known. They're the Ohm laws. So I1 would be VT minus V1 divided by R1. I2 would be VT minus V2 divided by R2. I3 would be V1 minus 0 divided by R3. I4 is V2 minus 0 divided by R4. And finally, I5 is equal to V1 minus V2 divided by R5. That concludes step number 2 of our algorithm. Let's count the number of unknowns that I have in the circuit. So assuming that VT is known, because one of them has to be known and then the other one would be calculated. Then I have 1 IT, and then 2, 3, 4, 5, 6, 7, 8 unknowns, which include 5 currents and 6 currents and 2 voltages. And then here I have 1, 2, 3, 4, 5, 6, 7, 8 equations. So this set of equations, once I solve it, I can calculate everything as a function of the knowns in the circuit. And the knowns in the circuit are the values for the resistor and the voltage VT. In other words, now I can calculate IT and all the currents in the circuit and the voltages once I solve this set of equations. Now, solving this set of equations is not very simple, even though it's not that difficult too. So one thing that you could do, as you notice, I have an equation for all the currents in the circuit, all 5 of the currents in the circuit as a function of the voltages here. So what I could do is to take all of these and put them back in these 2 equations and pretty much get rid of 5 of the equations in the circuit immediately, which would leave me with 3 equations with 3 unknowns, IT, V1, and V2. And at that point, I'm dealing only with a set of equations, instead of equations with 3 equations in it, which is not that difficult to solve. My point at this point is that the circuit analysis component, for the most part, is done. What's left is math, and how you do the math is really, there are a lot of options. You can use your calculator if you want to. You can use the linear set of equations solution that I explained to you how it's done using the matrices. So the physics part of the problem is all over, and what's left is just doing the math. Nevertheless, doing the math with hand, it might be just time consuming. So let's see if there are things that we can do to kind of quickly get to solving this. And actually, there are ways that you can do that. There are shortcuts or tricks that you can use to basically deal with a circuit like this. Some of the shortcuts that we learned were to use combining the resistors to each other. Like if there are resistors in series or there are resistors in parallel, we combine them to reduce the number of components in the circuit, and that way we get a clearer look at the circuit. Now, let's see if we can find any of those combinations in the circuit that we see. So for the components to be series in series to each other, there should be the same current passing those components that we assume are in series. So let's try. Can we say that there are any two components in this circuit that pass exactly the same current? Let's just pick two, R1 and R3, for example, where, well, they're obviously not passing the same current because I1 is going in and there are two currents leaving that node, so these two are not in series. These two are not in series. These two. Any combination of the two that you pick are not in series to each other because they don't pass exactly the same current. In terms of being in parallel, we mentioned that they have to share two nodes, and that's basically means that they are sharing the same voltage. So let's see if they can find any of two components that have that situation going on. So R1 and R2, they share that node, but not the other end. R2 and R5, same. Again, any combination of any two of these that you choose, you can quickly realize that they don't actually share both nodes of the two end of the components. So no two components on this circuit are in parallel either. And that leaves us with a situation where we can't really use any of those tricks that we have learned in order to simplify the circuit. Now, there's this other way of doing the simplification here, and that's when you can take a different kind of combination of resistors, and I'm going to draw that somewhere here. So take those three, so R1, R2, and R5. Connected to each other like this. There's this equivalency where you can turn a connection of resistors like that to a connection of resistors like this. I'm going to call that RA, RB, and RC. Okay? There's a name for this. This is called the delta to Y transformation. So you can equate a combination of resistors that are connected in kind of a rectangle like that with the three terminals on the three end to another connection of three resistors to each other with the three terminals, where you replace the resistors connected in a triangle to connection of resistors that are kind of connected in a Y shape, or a star shape, right? In the middle, there's a connection next there, connection compared to what you had over there. And you can actually write the equations for these two and figure out how the value of RA could be calculated as a function of R1, R2, and R5. In this case, I just used the same names for that. Now, it might be better if I generalize this and call it R3 and then go back to R5 when I'm in that circuit. Okay, and to do that, I'm going to write the equations here and maybe later on show you how this is calculated. So the RA in this case, it's actually equal to R1, R2 from that over R1 plus R2 plus R3. You can repeat that for any of the same kind of take. So equivalent of the circuit RA would be these two resistors that are used to be on the side divided by all of them added to each other. And then RB, same story. So R1, R3 divided by R1 plus R2 plus R3. And then finally I'm going to put it up here, RC would be R2 R3 divided by R1 plus R2 plus R3. If I use this and implement that on this circuit, I'm going to replicate the same circuit down here. So I'm going to replace R1, R2, and R5 that are kind of in a delta or triangular shape into that star shape or Y combination, and then connect it to the rest of the circuit. So I replace that with this. I'm going to call these the new names RA, RB, and RC, and then leave the rest of the circuit intact, R3 and R4. So this is equivalent to that circuit, assuming that I use these three equations to calculate RA, RB, and RC as a function of the original values R1, R2, and R5. Now what does that mean? That means that RA would be R1, R2 divided by R1, R2 plus R5. And then RB would be R1, R5 divided by R1 plus R2 plus R5. And RC would be R2, R5 divided by R1 plus R2 plus R5. Now, the nice thing about this is that now if I look for components that are in series or in parallel to each other, I can actually find some. So look here. RB and R3, they actually pass the same current. If I put note there, you can clearly see that they pass the same current. So what I can do is to take these two and put them in series and turn them into only one resistor. Same here. I can do the same to these two resistors. Once I do that, then these two resistors actually end up being in parallel to each other because they share two nodes on the two ends of them. And then RA is going to end up being in series with the whole thing. So I can quickly actually calculate the equivalent resistance there using these combinations. So let me try and write that here if I can. So that would be R equivalent equal to RA in series with these two in parallel, right? So that would be RB plus R3 in parallel with RC plus R4. And we're done. So I calculated the equivalent resistance. I have to use these equations to kind of calculate, turn this delta or triangular shape combination of resistors into a star or Y shape combination, and that way I can simplify the circuit and calculate the equivalent resistors. Now, obviously, in order to be able to do that, you have to memorize these equations, and that's why I'm not such a big fan of this, because if you don't use this frequent enough, there's a really high chance that you're not going to be able to remember these equations when the time comes to use it. But if you just go back to basics, well, it's true that you have to do more work in order to calculate the equivalent resistance, because at this point then you have to solve this set of equations. There is no memorization involved, but you still have to solve that set of equations. But the good thing is that there is nothing to really forget about this once you keep on practicing the same. Maybe the only thing, well, KCL is really intuitive. Maybe the only thing is Ohm law, but really as electrical engineers, you're at least expected to know what the Ohm law is. And from that point on, you just do the math. And I promise you that once you do the math, you're going to end up calculating VT divided by IT or R equivalent to be exactly the same as what's written here. Well, obviously you don't see like this. It would be actually a complicated equation because I'm still using these notation, the parallel combination of these two. So in reality, the equation is this value in the parentheses multiplied by this value in the parentheses divided by the two added to each other, which then ends up being a lot more messier than what you see here. But they're definitely equal to each other once you do the math over there. So with that in mind, what more I want to do at this point is to tell you how you can calculate these equations off of this equivalency, which might be useful. And for that, here's what you need to do. So let me clear this and kind of explain to you where these three equations are coming from. The math or the circuit analysis or associated with calculating these three equations. So you look at these three nodes here. You call these three nodes three names. You call them A, B, and C. And obviously, with the equivalent to each other, these have to be the same nodes. And then you say, okay, if these two are equivalent to each other, therefore, the resistance that I see from any of the two terminals out of the tree would be exactly the same, have to be exactly the same. So you look at the two terminals AB and calculate the equivalent resistance looking from AB, and you do the same for this one, and you equate them to each other and repeat that for the other two combinations out of three, and by doing so, you get three equations. So let's try that. So looking from AB, the resistance that I see would be R1 in parallel to R2 plus R3, if you agree. So these two are in series to each other, and then the result is in parallel to that. So I just write that. I say RAB, looking from AB, that would be R1 in parallel with R2, R3, I'm sorry, R2 in parallel with R2 plus R3. And then looking from AC, the same thing, that would be R2 in parallel with R1 plus R3. So R2 in parallel with R1 plus R3. And finally, looking from BC, you would have R3 in parallel with R1 plus R2. Okay, so now you repeat the same thing from this one, and you say, okay, RAB here is something else. So what is that? RAB in this case, looking here, leaves that with an open circuit, so it would be RA plus RB, right? And in this situation, so that would be RA plus RB. For this one, RAC from this circuit would be RA plus RC, RA plus RC. Then finally, for that one, it would be RB plus RC, RB plus RC. Let's make sure it's clear. Looking from these two, terminals right here, when you want to calculate the equivalent resistance, that terminal just stays open. It's not connected to anything. So there's no contribution of RC looking into RAB for this circuit. And at that point, just these two are in series to each other. And the same for the other two terminals. Now, once you do that, you have look at these. So you have three equations that relate R1, R2, and R3 to RA and RB. And if you assume out of these two sets of resistors, meaning R1, R2, and R3, RA, RB, and RC, if you assume one set is known and the other set is unknown, then you have three equations, three unknowns. You can calculate the knowns as a function of unknown. And you can do that both ways, meaning that you can actually calculate RA, RB, and RC as a function of R1, R2, and 3. Or you can calculate R1, R2, and R3 as a function of RA, RB, and RC. And these two, once you calculate these as a function of the three R1, R2, and RC, this is called a delta to Y transformation. And you actually switch and calculate R1, R2, and R3 as a function of RA, RB, and RC. That's called Y to delta transformation. And you can find the equations for the other way around anywhere online or in the book. But my point is, if you know how to do math and you do want to still use this trick, and you don't remember what the equation is, it's just the result of solving this set of equations and find one set of the resistors as a function of the other set, which wouldn't be that difficult. Thank you for your attention. We're going to continue in the next lecture.